today, so we should be able to finish up all the presentations today, and then yeah, Friday we have to wrap up. Okay.
So hi, we are Group 5, and we're here to present to you our case study, Integrated Geophysical and Geotechnical Investigations of Old Mansory Retaining Walls in Hong Kong. So the first step of our investigation is the setup. Many heritage buildings in Hong Kong used retaining walls during their construction. And this leads to many consequences in the future, as excess poor water pressure and just the relative age of these walls deteriorates their structural integrity. So this leads to our problem. Which geotechnical techniques should we be used to determine the conditions of the Mansory walls? Okay. So our main properties for this investigation are dielectric permittivity and electrical resistivity. And our main materials that we're working with are air, water, clay, stone, and granites.
Okay, so in 1984, one of the walls collapsed of Mansory. So what they did was they wanted to determine if geophysical techniques would be good to identify different characteristics about the wall. So they took a already collapsed wall and they conducted a GPR survey along it. So what they did, so this is the top of the slope right here. You can see these are the trees right there. What they did was from the top of the wall, they took a GPR survey down the surface of it to determine the depth of the wall as well as different characteristics such as pore pressures, etc. And for the EIs, they use a runner array to determine the electrical resistivity of the boards. And so the data that they got was, as you can see here, they didn't have any real data diagrams provided about the electrical, from the DC resistivity, but they did provide the GPR ones. So as you can see, I can't read it here, but I believe right here they were able to identify a void. And in the paper, they also mentioned in the top couple surfaces, they also found many areas where there were a lot of voids. Also, you can see down here there are larger voids as you go deeper into the wall. Okay. So to process this, they took the pseudo depth section and then they filtered the data with digital gain adjustment, filtering, distance corrections, and spectral analysis. And they did an inversion for the EI data, as you can see right here. Perfect. So when they took the data, they found that the base of the wall had a lot of voids. The amount of voids increased as wall depth increased, and that they found a lot of voids in this northwestern section here on the wall. One of the things was because the wall was against a slope, things such as the ground could affect the GPR survey as well. And what they did after was they took measurements from the wall to determine if the characteristics were similar to what they obtained from their geotechnical techniques, and they found that it was relatively well done, except for the GPR made the unreliable. I mentioned that they didn't take into account that the wall was lying on a cut thick, so differently bedrock that could affect the GPR signal.
Thank you.
So I couldn't quite see the scales of things. So the voids or the sort of construction in wall, did that come out as really high resistance?
For the EI, they found that, but in terms of resistivity, they did find that the core pressure was fairly high. They did, I can't remember correctly, they did find most of the voids were filled with water, and that's mainly due because there were trees in the area so the groundwater were seeped into the voids. They didn't provide any diagrams for the EI specifically, as the paper generally talked about the GPR. So that's, yeah.
Did they talk about sort of this interesting sort of pull-up right in the middle? Did you call that a trough? I can't read.
Top of granite slab over.
Yeah, so what's happening right in the middle is.
Yeah, I think it's a sewage pipe.
Granite slab.
I'm sorry, I can't read either.
I think it says that.
Don't worry about that.
Hey everyone, so we're group 15, Yusuf, Muin, Rita, Stephanie. We're going to talk about everyone's favorite dam, Mount Holly. Probably heard about this before in some other class. We're going to talk about kind of the geophysics that went into the investigation. So we know that a failure occurred in Mount Holly in the glacial lacustrine layer underlying the upper till that was underlying the foundation of the dam. And we wanted to see if geophysics could find that glacial lacustrine layer. And there was also another independent report after the dam failed that tried to find this same layer. So this is the general case. We'd want to see what we would do differently before the failure, before the dam was even set up, so we could identify potential glacial lacustrine material.
A quick glance at the physical properties of the glacial lacustrine layer and the till demonstrates that resistivity and chargeability are really the only ones that'll help us identify. The independent panel did a resistivity, but also a seismic velocity. As you could guess, the seismic velocity did not reveal any data, but the resistivity and chargeability surveys were too noisy to actually gather useful data. While the specific surveys that they did were not clearly described, a future survey for resistivity and chargeability could be the gradient array and the borehole survey.
So we were able to use the seismic applet on the GPG to demonstrate that when you don't have contrasted velocities, of course, you're not going to be able to have interpretable data. Slide. And for their resistivity surveys, unfortunately, they encountered excessive noise. So greater than 10% of the total amplitude ended up being noise. So they decided that the results were not useful. In the general case, ideally, we would have an apparent resistivity pseudosection with low amounts of noise. And for processing, the independent panel decided to take the seismic and resistivity data and invert it into 2D cross-sections. And a possible GPG applet use for the general case would be the parametric conversion DC app. However, as is, it would be valid only for a simple horizontal 2-layer Earth model. So we would need more complex geometric capabilities because in the real case, glacial lacustrine often varies quite a lot laterally, so it pinches out and thickens.
Yeah, so we determined that due to the high noise, high variability, and this properties being too similar at the surface, the glacial lacustrine layer couldn't be identified. So therefore, for better interpretation, we suggest that geophysical survey done will head when mining activity begins, so that the noise can be avoided. And to get a better idea of chargeability and low resistivity, we recommend that core drilling and other pore water pressure indications and other methods should be used to find the intersection between flow resistance.
Any questions?
In terms of both the resistivity and chargeability, can you comment about the contrast, what you guys are looking for?
Right. Do you want to?
If we head back to
This slide.
right, so here we can see that chargeability is very high in the glycolacustrine, and that's because the glycolacustrine is mostly clays and such, whereas the till is harder sediments with lower chargeability, and vice versa can be said for the resistivity.
So you're finding a conductor and high chargeable, conductive and high chargeable, right?
Essentially,
Yeah,
yes.
low resistive areas and high charge.
Granted, the glacial setting is very, very messy. So even though these seem to be having a clear distinction, it could be very interchangeable between the two.
And how that kind of unit can make an impact for the breakdown of the non-poly? Can you explain why that unit is important to characterize?
Right, so these properties aren't why the layer failed. It's the glycolacustrine layer is clay, which when it was loaded, and you guys can comment on this as well, essentially acts as undrained. So it suddenly, how do you describe it? Almost solidifies.
Yeah, so like the excess pore water pressure response is something that's really crucial when monitoring like dam slopes, dam foundation stability. So the glacial lacustrine, because it can generate such high like levels of pore pressure as in contrast with the other till units, is what makes it interesting and of concern. So it's really fine grained as opposed to all the sands and gravels and tills that are over and underlying it are much coarser grained. So you can imagine water is able to drain more freely.
Okay.
One quick question, just how thick is that layer?
It's very thin.
It's thin, but it varies.
Like thin, like meter or 10 meters or?
Typically around, I think, a meter was what we were getting.
Yeah.
Maybe like between 5 to 1 meter, I think. And then in some places it was a bit thicker.
Yeah,
But
this wasn't like the ideal, like it was sporadic, like it would pinch out from like a meter to maybe like 0.1 meter.
Okay, so that's not too.
Yeah, it was not uniform at all.
yeah, and the study couldn't find it. We can't really tell in retrospect whether it was because of the noise or because of the thickness of the layer, but most probably it was because of the noise of the mine operations and the mine equipment that it wasn't able to be found. Julian?
If you were to do it again, you mentioned that there's too much noise, how can you change the survey so there's less noise?
We suggested that the survey being done well ahead before mining activities began. That was the main problem. That's why the seismic refraction failed. Even though they did it, they couldn't identify that tiny layer. And later on, when investigation was done, they found that that was the main reason. They could have avoided it like well ahead if all the surveys were done well ahead of time.
So I don't think the change would be to the survey itself, but rather the timing of when we do it. All right, thank you.
Yeah, Doug. So we're doing
Oh, that's fine, no problem. We'll have two renditions.
Yeah.
Another round ball.
That's the slider.
This.
Yeah.
Okay. Hey everyone, we're Team 1, and today we're going to be hypothetically using a historical situation to apply our geophysical knowledge, namely the 2014 Mount Poly tailing storage facility disaster. So as a bit of background, as some of you might know, it was triggered in part by an unknown glacial lacustrine clay layer about 8 meters deep that failed under shear. It wasn't found in the initial site investigation, which include drill holes and test pits. So they couldn't design the dam to accommodate for it. So what we're asking is, in the 90s, in initial site investigation, if they used geophysics, would they have found this GLU layer? And here you can see the layer right there, and this is the failure.
So as introduced a bit before, the upper glue layer was an undrained pre-consolidated clay that's in between the confining glacial two layers, and they're different in water content, density, and porosity. So physical properties used here are the electrical resistivity and the seismic velocity.
Yeah, so the hypothetical survey we're using is the DC resistivity and seismic reflection. So we start with the DC resistivity.
So for the DC resistivity data collection, it is important to obtain data for all depth down to bedrock level, and the weather rates are reclaimed for sounding process, and the glacial acoustic unit should demonstrate a lower resistivity than the surrounding tier. We could use two-layer app to obtain some message across. During sounding, upper limit of the GLU layer should be classified as that, where apparent resistivity decrease significantly, and the bottom limit should be where apparent resistivity stops decreasing with increased investigation depth, which indicates a higher resistivity tier.
For the seismic reflection data, we know that the upper layer is tone, so it's higher in seismic velocity compared to the GLE. GLE has a lower seismic velocity, and so what we're looking at is only the reflection, not the diffraction, because lower velocity underneath the surface would results only in reflection. And so we propose that we use the common midpoint survey data, and as you can see there that if we have a dark zone, then that should be the one that we're focusing on. That should be indicative of the GLE unit.
Yeah, and so because we're analyzing a what-if scenario, they didn't have the 3D data processing power back in the 90s to really do a proper inversion, but they should have still had some basic geophysical knowledge to conduct manual interpretation of the raw data. And this would have allowed for the geotechnical engineers on the project to have a little bit more of a backbone when approaching the client to ask to go for deeper boreholes and test pits to try and find that layer. And it would have given them some areas that they would have likely seen that area. That's it.
Anyone have any questions?
Do you know, was there geophysical data taken there at all?
They only did drill holes and test pits,
At
kind of
first?
randomly too, like not really any system to it.
Were those drill holes and test pits done like right in the region, or right over the place where the dam?
If I recall, they
fails?
weren't deep enough. They weren't deep enough to find it.
They were at the locations that shallow. So I guess the thing is that if they had the geophysical data, they would have been able to go to the client and ask for more money to maybe get better drill equipment to site to be able to reach those deeper areas.
And instead of just spraying and praying drill holes, they can actually focus on areas that probably have something of interest.
Thanks, Maxie.
Give you a photo. Oh, yeah. We'll tell them right when it starts. This actually work. No, let's use the computer. This is like a There you go. All right. Hey everybody. We're group 14. I'm Gavin. This is Cal, Connor, John, and Kelsey. The questions that we're going to ask today are: how can we use geophysics to determine regions susceptible to wildfires? What can geophysics tell us about wildfire behavior over different surface conditions, such as moisture content in the soil? Can geophysics be helpful while fighting wildfire? And how can the DC Layered Earth Resistivity app help solve these questions?
So in terms of physical properties, these are the two main ones we're looking at. Obviously, electrical conductivity is going to be higher in a saturated soil, and then that's due to dielectric permittivity of water being higher. We can use GPR to get the depth of the peat layer, and then DC resistivity to calculate how much water content there is.
We did make a slideshow.
And now time for the video portion.
Holy shit, that's awesome.
What's up?
Do you guys want to use your? Yeah, you know.
Everybody knows on their sheets and like presentation.
Okay, we're back. We decided to use the gradient array survey because it's really fast to get huge amounts of area, which is good for firefighters to get like rapid information. And the depth doesn't matter as much as the water content does, so that's why the depth information isn't a huge deal.
So we're going to need to make some assumptions on what parameters we're going to expect. And we consulted a study done by Pontiani et al. In the University of Delft in the Netherlands, and they found that the conductivity of peat is directly related to the conductivity of the groundwater and also the water content of the peat. So assuming approximately resistivity of 50 ohmmeters for the groundwater, and a water content averaging 90% in the top of the peat, using the models they created empirically in their study, that gives about 75 ohmmeters resistance for the peat. If the water content is very low, around 10-15, we might have 50, and high water content is past 100, can yield up to 200 ohmmeters resistivity. And for the data, we're going to be doing some QC and visualization. Basically, what we need to know is if it's going to be within what our model expects, and we'll be testing it in the Layered Earth DC Resistivity app.
Yep. So for the Layered Earth DC Resistivity app, we're going to say that the peat layer is going to be really thin, around 1 meter, and depending on the relative amount of water saturation, that will change the resistivity that you're going to get back from the survey.
Okay, so for processing, we're going to make it 3D, so try to visualize it more. Also, we're going to be looking at the shallower layers because that's what we're interested in. We're interested in the forest floor, which we're approximating as peat. But if there is anything deeper, then we kind of want to know about that. It could be kind of a question mark. And then next. So, and then synthesis, like basically, we just want to know, like, is it true that the surveys that we're doing? And so ground truthing,
go actually check some soil like moisture content, see if that is true, to see if the data we're getting is reliable. That and also just like in British Columbia right now, forest fires are a big problem in the summer. So anything that could be done further, potentially with geophysics to relate to it, could be useful. So, yeah.
One of your questions was, can geophysics be used to fight, like actively fight wildfires? Like, could you? But what's the answer?
Oh, that was like how, like, can we use the geophysical data and like send it in like real time to wildfire fighters on the ground? That just depends on how fast you.
So you would have had the data beforehand then.
Yeah, like if you know a wildfire is going to like spread into a certain area, you can set up a geophysical survey there and then get that data to the wildfire fighters and say it's going to spread at this rate in this direction, that sort of thing. So
the survey measures the resistivity of the peat, and that is related to the water content. And more water content in the peat, the fire will spread slower through that area. So we can find which areas are of most susceptibility to rapid spread, and we can know where to focus the firefighters.
Yeah. Are there many fires in peat landscapes, BC?
The peat was like, there were only like references for these surveys with peat. That we couldn't really find anything for other fuel types in British Columbia, so we just kind of approximated all fuel in British Columbia as peat. Not ideal, but.
So if we were to look at all these devastating fires that we've had over the last 2 summers, and if you're asking, okay, how are these fires spreading? Are they actually burning on, spreading by burning on the ground, or are they just kind of going tree to tree to tree and it's just being wind driven? Does that sense of that?
Well, it depends heavily on like the area that the fire is moving through. Like if it's a very heavily forested area with lots of like thick crown, like the tall trees and lots of needles and things like that, then the fire will move through the crown very quickly, but it'll also burn all the superficial fuels usually first. It always depends on the wind speed and how hot the climate is in the area, and obviously the moisture content of the fuels as we're finding out here.
So have other people looked at this aspect, moisture content?
Yeah, back in like the 60s, there were some foresters who went out and did a lot of just lighting fires and figuring out how to, like in like a controlled environment, they would light a fire and they would like find out how fast the fire spread through the area, and they would know the moisture content and the temperature and the wind speed in that area in a controlled environment, and then they would put that into an empirical model, and that's what firefighters use today. But this is like using data in real time to hopefully improve that model.
That's an interesting example for these. Okay.
Alright, so as you guys can probably tell, our project's a little different from most people's. We're trying to find what the perfect avocado is using seismic geophysical methods. And what we mean by the perfect avocado is the one that has the smallest seed and the highest amount of flesh. So basically the lowest mass seed to total mass ratio.
Okay, so how do we use geophysics to solve this problem? we figured, we're going to use some seismic reflection, and grocery stores aren't big when you're using invasive methods such as drilling into the avocados. So we're going to use geophysics and see if we can get a good idea of what's going on. Before we do any geophysics, we need to get just test avocados and do some lab tests to find what's the density of each of the parts. What's the density of the skin, the flesh, the seed, and we're going to assume, for the sake of simplicity, that the seed is round. So.
And for the physical properties, we're gonna use a seismic survey, and we're gonna expect to see like different densities between the flesh and the seed, and we're gonna record the travel time. And also, like we said earlier, we want a low impact, not to bruise fruit.
So here's an idea for a survey. Our options are either using a very small hammer or perhaps something to induce vibration into the avocado. And we're going to do at least 2 tests so we get like a good estimate of what the radius of the seed is going to be. This is all just preliminary, and we suggest contacting your local geophysics consultants and see what their small scale prices are. So we need to find the mass of the avocado to compare to the seed. And ideally, we're going to get the 2 tests and a little bit of repetition on this slide. Here's what we took from the app, and this is just a qualitative slide here. We expect to see the density of the seed greater than the density of the skin is greater than the density of the flesh, and that's why you get the negative reflection coefficient going from the skin to the flesh and positive from the flesh to the seed. So we hope that this has been a lot of help for you, and you keep this in mind the next time you're in the grocery store and you find a good avocado. Any questions?
Are you taking the pit out and passing that?
In the beginning, we're going to take a pit. We're going to measure the volume and measure the mass, so we have an idea of what the density of the pit is, so we can inspect that.
Taking the pit out.
This is a dry test to get our values that we need to go on and do this many more avocados. Oh no, this is just a dry run. We're gonna get an avocado that's not having geophysics applied to it, so we can define the properties and get a better model of the avocado.
So to clarify, you mean that there's a sacrificial avocado?
There is a sacrificial avocado.
At least one.
How do you think ripeness affects seismic velocity?
That's a good question. We count on avocados needing to be shipped relatively unripened, because if you ship them ripe, they get bruised. So we're gonna assume just a blanket density. Andrew.
Would a hammer bruise the avocado?
Very good point, but very small hammer, very lightly. Exactly. It is a consideration, because that is a good point. It might, but this is just an idea at this point.
Thought of the resolution, because it's not like a generating actually seismic source wavelength have very you probably need to have very high frequency to resolve that thin layers. Have you kind of thought about that?
I have considered that, and I have considered simplifying the skin and the flesh as to just one layer, or just ignoring the skin, see if that gives a more reasonable result.
So, like with that, it's like kind of what kind of frequency? Like, have you kind of computed? Oh, I probably need to use this source frequency to resolve that layer.
I've not considered that, but I'll keep that in mind when I.
Tough one to follow.
Which one's next?
Okay. Hi everyone. We are group 13. We are talking about how geophysics could have been used to confirm the presence of water on Mars. So the background is that a NASA rover discovered a mineral on Mars which only forms in the presence of acidic water, which proves that water once existed on Mars. We wanted to use geophysics to confirm if water still exists on Mars. So because dielectric permittivity is much higher in water than dry rock, this is the diagnostic property we chose.
And because dielectric permittivity is a diagnostic property, it makes sense to go with the GPR survey. We expect water to form a planar feature under the ground, so we could use a common offset survey. This could be a zero offset survey like what we have in the apps, and you could take the same shot of the same location to help you stack the data later and get rid of the noise.
And for data, we're going to try to cover a large area, as large as possible. And we're expecting minimal noise as there's not much human interaction on Mars itself.
So for our processing, we just need the travel time to be converted to depth so we can find out to what depth the water is at. And then for additionally smoothing up the data, we can use stacking and smoothing to get better results.
If there's
noise. If there's noise. For our interpretation, we just want to confirm our findings by the spectrometer images from NASA as well, so that's a confirmation for us. For the app that we're going to use, something similar to the setup for the Lab 6 fit data, where we would see a planar feature for the water. And the main questions we're asking is, does it make sense for water to exist here? And is there evidence from other investigations for water to exist?
Thank you for listening.
So have you thought about that kind of scale that you want to map up? And also, like, if you really want to cover a large area, because Mars is pretty large, like, have you thought about what kind of instrumentation, like, you want to use? Like, attach the GPR to somewhere? Like, have you thought about that? Kind of details?
We think it would be cool to have the GPR on like rovers that can move around and they're robotic and can be controlled from like an astronaut.
Okay.
And I guess the scale then would depend on how much the rover can move. So wherever the rover goes, you survey.
Okay.
Yep.
We know there is frozen water on the caps. Could you use a similar survey to learn more about caps like that for example?
That would be cool.
See, the temperature on the surface of Mars varies a lot. And it could be liquid water during the day, and then it could be frozen water during the night, and then it could change. But we're expecting like a surface if we can.
What was the mineral that was found that you guys studied?
GeoSci.
What is it?
Oh, like the chemical formula?
It contains iron. That's all I know about it.
If you guys find water on Mars, what are you going to do with that knowledge? Drink it.
Sell it to NASA. Okay. Cool.
Hi everyone, we are Group 6, and our topic is using geophysics to expand the mining perimeter in Untitled mine in the Northwest Territory. We're interested in finding the new underground intersection of the tungsten ore, which are scheelite and pyrrhotite, where the hosting rock is highly altered limestone. In the meantime, we have some rock sample passing along. You guys can see. That brings us to the second set, physical properties. The biggest contrast would be magnetic susceptibility, chargeability, and resistivity, where the ore has high values in magnetic susceptibility and chargeability, and the host rock has low values in both of them.
Okay, so for our survey design, we're going to have quite a few challenges as we're trying to do geophysics underground. We got our small working space, and there's going to be interference from mining activities and infrastructure like rebar and wire mesh. So we'll have to account for that. Our solution is to do a DC and IP borehole surveys to hopefully get a bit further away from that noise. We'll be going into the wall rock, looking for these chargeability and resistivity contrasts between the ore and the background, highly altered limestones. And core drilling is already done in the mine to expand the resource, but we could use those similar holes for these surveys themselves. Since we have limited space working underground, we want to use a dipole array setup like Schoenberger or Leonard, and then we'd be measuring voltage drops and changes in voltage. And it's interesting to note that since we're doing borehole surveys, we can do them in almost any direction. We could do them down, we can do them into the wall, we can even do them up. So we could get a really good idea of the extent of ore underground. For data processing, we have a lot of information that we know already because it is a mine that has been in operation for a long time. So we can use all these for inversion, and it's really well known. So currently the DC app on the GPG doesn't have the capability for borehole setup survey, and similarly we would need an IP app to do the same thing. The types of data we'd be expecting would be very similar to what we can get on the app right now. This is an example of a highly conductive ore body and a really resistant background, just showing basic profile. And then similarly, the chargeability data we'd be looking for would be like this from an app. In synthesis, we can use geophysics to locate ore bodies underground using DC and IP, and hopefully the noise won't be too much. And we need to make a new app for this, but I know you guys are up to it. There's some lovely sources. Thank you very much. And any questions?
Have you tested either of the limestones to see if they're related with halite or silvite at all?
No. Have you been licking the rocks?
No, I'm asking if you've licked this.
I haven't licked the rocks. Any other questions? All right.
What's the economic outlook on tungsten?
Tungsten, right now, not very good.
Right. Yeah. I looked up a graph here from like 1940.
Yeah,
it's not like an all-time low.
Yeah. We're waiting for those prices to just go right.
That's true.
So it's an in-mine setup, right?
Yeah.
And then you're like, you need to drill a hole to do a borehole survey. I kind of thought about what it could look like and what are the, like how deep you want to drill it and.
I was thinking personally, just what I was thinking was like a dipole array, but the whole array is set up inside the hole, so you could move it along inside, and so you can go as deep as you want. and just kind of shift them along and move them back and forth and take them back out and get the data in like a 3D around the hole. Where
So you'll drill like a kind of.
no, just one hole, but you get 3D data representative of a certain radius outward from that hole through the whole thing.
So if you drill that hole, then you'd like to make as much use of it as possible.
Yes.
So what you proposed is actually a reasonable thing to do. Could you think of something else that you could do with that hole with respect to how you're going to place your currents and potential electrodes?
Not quite sure exactly what your question is.
Well, you have a hole going in, right? And then you've got currents and potential electrodes along it. That's perfectly good. That's great. But it was expensive to drill a hole. And now the question is, could you get additional information? Could you take additional DC data somehow by changing where you put your electrodes? And if you could do that, do you have any idea of where you might want to put them and why?
Probably further in the hole to be reduce the noise component from all the mine infrastructure and activities would be better. You get cleaner data. And the thing is, they're already drilling all these holes for like resource mapping underground to find where they are anyway. So they're doing it already, so we can use the same holes for our surveys. So it's not quite as expensive. All right.
That's a good one. Okay, we are group 11. We're going to talk to you about geophysics applied to the Millennium Line Extension. This is a project that I know a lot of you are very familiar with. The MLBE is a $2.83 billion transportation project by TransLink. It's composed of 700 meters of elevated extension, 5 kilometers of underground tunnel, 6 new stations, one of which is connected to the Canada Line. Therefore, it's a huge project, a lot of construction underground. We need to characterize the site. As we know, also from our studies with GPG and our labs, the False Creek area is very complicated geologically with a mix of glacial and river sediments, lots of dipping layers and buried objects, which makes it difficult for construction, so we need to know what's underground. Also, the region has numerous creeks that have been filled in. This is important that if we're boring a tunnel underground and we reach a big boulder or rock, that can be disastrous for a bore machine stuck underground. So as you can see, this is the setup. VCC to Great Northern Way is the above ground. Everything else is below ground. Hopefully we get the extension line extended to UBC one day after we've all graduated.
Cool. So then continuing on from that, it follows that our main objectives would be to find the depths of the glacial and alluvial till of the sites of the proposed underground tunnels. In doing this, it'll be more or less an anchor point for future drillings or surveys when the line comes through. Additionally, it'd be a good idea to find the thickness of the river sediments because that will allow us to quantify how much extra consolidation is necessary when we start building. Secondary objective, of course, those large boulders and other debris infrastructure along the False Creek area. Those might get in the way, so something else to look forward to. So, propters. Because we're looking at depths and thicknesses and that sort of thing, we thought that using seismic velocity would be a good idea. This is also supported by laboratory findings that the glacial and alluvial till actually show quite a significant difference in their seismic velocities. This is shown glacial till has seismic velocity around 450 meters per second, while the alluvial till has a mean around 1,310. So it provides a great contrast for us.
So going with a seismic survey, we wanted to go, first of all, with a reflection survey. Mostly just because we're just interested in the depths of each layer. We're not really looking at porosity or anything. So a reflection survey would be best. And then we would also want to use a common midpoint survey, mostly because we're mostly interested in where the stations will be primarily. And then after that, we'll look more for the tunneling, yeah. And one more consideration is that there is a lot of steepness in our terrain, so we'd have to take 2 shots at each end around our point of interest to categorize that.
Alright, let's blaze through this. Data. So we're expecting like a 15-meter-ish kind of depth for the alluvial till on top of the glacial till. So problem with this is that the seismic reflection survey wouldn't really reach, the refraction survey would actually reach the receiver in time, according to the app. So here we're going to use a reflection. This is why we're going to use a reflection survey, and then an improvement on the app would be probably just extending the offset so that we can actually find the intersection between, or like the points where the reflection and the direct wave meet. And then, yeah, I'm just processing normal, just canceling out the noise, NMOs, enhancing the data. And then, so basically what we are expecting is like 2 layers of deposition, and 2 layers of deposits before hitting bedrock. And then based on previous Canada line, they drilled to the depth of 60 meters. So we are expecting no bedrock over that, just till, which is good for us. And then one more thing is also near the old razor, the valley. What's it called? Creek. So basically near where the above, like the Fall Streak area was filled in, and we probably need to drill deeper to find out where like the suitable depth of the power would be at.
In terms of synthesis, the seismic reflection would be good for determining the depth of the layers, which is great for drilling. If you want a better understanding of the surrounding geology, you're going to need different geophysical surveys.
So you're saying that all the tunnel will be above the bedrock? Do you
we are
know that for
expecting,
sure, or are they interested in what the depth of that bedrock would be?
Yes, but that would require a different kind of survey because the seismic survey wouldn't go that deep because we're expecting like 80 plus meters of depth before hitting bedrock. So it would require more, like a...
The site's been characterized that like the depth in your tunnel will be well above bedrock. So they're interested in characterization.
Okay, guys, thanks very much.